Now this brings us to something interesting we can do in Python. Remember, we said last time that when we create a variable name, we're basically creating a pointer to some location in memory. So here we create the variable myInt1 and set it equal to the value 5. So we now have a variable called myInt1, and it points to a place in memory holding the value 5. However, we noted that it's possible that we could have multiple variable names pointing to the same place in memory. If we created myInt2 and had it equal 5 as well, it would also point to that same location in memory storing the number 5. What that means is that the computer has to have some way of identifying this location in memory, besides that particular name. Multiple names or different names can point to the same place in memory, so the place in memory really needs a fundamental, unchangeable name. This is called a memory address. It tells the computer where to find a particular value for a particular variable name. Python lets us print the memory address for any variable we create. So here on line 1, we create a variable called myInt1 and give it the value 5. And then on line 4, we print the ID of myInt1. ID is a function in Python that returns the memory address for a particular variable. In other words, it returns the place in memory that the variable points to. Or if you just put a value into that, it returns the place in memory where that value is stored. Here we see that the ID of myInt1, or the location of myInt1, is this number. So we can think of this kind of as the street address for this data. This data is located at 14075654448. That's how Python knows what value to get when we use a certain variable. The variable points to that address, and that address corresponds to some data. To use an analogy, the variable name is kind of like a person's name. The value is kind of like their house, which is where you might find them. And the memory address is like their street address. If I tell you, come visit me at my house, you don't know where to come unless you know my address. You might know my name, and you might know that I have a house, or I have an apartment, or I have somewhere to live, but unless you know the address of where I live, you don't know where to find me. And similarly, just as more than one person can live in the same house, more than one variable name can point to the same location in memory. My wife and I have the same street address, but we have different names. So that's like saying we point to the same address, and we have the same house. The same way, multiple variables can point to the same memory address, and thus have the same data. Now the usefulness of this is we can start to see how Python deals with different kinds of memory address issues. This top chunk of code demonstrates how this works with an immutable data type, and the bottom demonstrates how it works with a mutable data type. Line 1 runs, creates a variable called myInt1, and gives it the value 5. So we now have a variable called myInt1 pointing to a place in memory with the number 5. On line 4, we print the ID of that variable name, and it prints this number right here. So the address of 5 stored in memory is 14075654448. Then as we've shown before, line 5 then changes the value of myInt1. We now know that the way that works is it creates a new place in memory, gives it the new value, and tells myInt1 to point to that instead of the original location. Then on line 8, we again print the ID of myInt1. But remember, it's now pointing to a different location in memory. And as a result, we see exactly what we might expect. This memory location is different than the previous one. Specifically, the last 2 digits are different. So the value 6 is stored at 14075654464. A different memory address for a different value. So for an immutable data type, changing the value is kind of like a person moving. They're now in a different house with a different address. The second part of this code, though, shows what happens when a data type is mutable, meaning its value can be changed. Line 10 creates a list, which we'll talk about later, and gives it the value 1, 2, 3. All those are strings. Visually, that's the same kind of thing. We now have a variable named myList, and it's pointing to a list of values. This is the same kind of idea. There's some data stored in memory, and myList is a name that points to where that data is stored. As before, line 13 prints the address of myList, and it has this address over here. So the address for this list is 408858824. Then line 14 modifies the list. It appends the number 4. It adds a new item to the list. But what happens when we print the ID again on line 17? Unlike for integers, our ID hasn't changed. MyList is still pointing to the same place in memory. It just now has an additional value at the end of the list. MyList is a mutable data type, meaning that its value can be changed. So changing it does not change the address where the data is found. That differs from integers, where changing the value of an integer actually changed the address where the data was found. Note though, this only applies to changing the existing list. So append is a method, kind of like a function, that makes some change to the list. If we actually set myList equal to a new list, we'll find that its ID does change. In fact, that's exactly what's going on here. On line 1, we create a new list called myList, and we point it to that list of items in memory. On line 4, we print its ID, and we find that it's this. On line 5, we modify it again, and on line 8, we again find its ID hasn't changed. It's still pointing to the same location in memory. On line 9, though, we set it equal to a new list. That's different from modifying it with the append method. We're actually changing its value, not just modifying its value. We're changing what data it points to instead of just modifying the data in place. So this creates a new list with those 3 values and tells myList to point over here instead. myList no longer points to the original list. And that's confirmed when line 12 runs, because printing the ID of myList now results in a different value from before. So mutable data types can have their values modified, but if we reassign them to different data altogether, then it still assigns them to a different location in memory. Finally, it's this oddity of Python that makes this code do what it does. On line 1, we create a variable called myInt1 and set it equal to the value 5. So we create a place in memory, give it the value 5, and point myInt1 to that value. Then on line 2, we create myInt2, and it's also set equal to 5, so it also points to that same value. But note that the memory address corresponds to the data in memory itself. Let's say the memory address is 5612871. Notice that both myInt1 and myInt2 are pointing to the same memory address. And as a result, on line 5, when we print the answer to the question, does the ID of myInt1 equal the ID of myInt2? Our answer is true. Those 2 variable names are pointing to the same memory address. In other words, they have the same ID. Mutable variables, though, like the lists we talked about before, behave a bit differently. Here on line 1 and 2, we're creating 2 lists, myList1 and myList2. But as we see on line 4, they have different IDs. What that means is that even though they have the same value initially, they're nonetheless stored in 2 different lists. myList1 has its own copy of a list with the values 1, 2, and 3, and myList2 has another copy of a list with the values 1, 2, and 3. That means there are 2 different places in memory with the same value. That's why when we run line 6 to append 4 to list 2 and then print the values of lists, we see that only list 2 has the value 4 added to it. 4 is added to the bottom of list 2, but just because it's added to list 2 doesn't mean it's also added to list 1, because they're stored in 2 different memory locations. Python knows to do this based on the value on the right side of this assignment statement. It knows that if this value is of a mutable type, it should always create that value in a new place in memory. If, on the other hand, that value is an immutable type, like an integer, then it knows to go and check if that value already exists somewhere in memory. And if it does, point the new variable name at the existing value. That's how myInt1 and myInt2 end up pointing to the same location in memory, but myList1 and myList2 do not. The type assigned to the variable name dictates which way Python should operate.